I just want to welcome you all for coming to the Analogs Focus Group meeting. Thanks for those of you that are here live, that will hear Jim speaking today and can interact with him. And then this will also be posted online. So thank you to those of you who have come afterwards to watch the recording at a time that's more suitable for you. So I'm very pleased to help run this Analogs Focus Group meeting. I'm Jennifer Heldman. I work at NASA's Ames Research Center, and I co-lead this group with Darlene Lim, also from NASA Ames, and Tim Glotch from Stony Brook University. And so this Analogs Focus Group, we want to thank our sponsor, which is NASA's SSERVI, the Solar System Exploration Research Virtual Institute. And so thanks very much for SSERVI for enabling this group to function, and to Ricky Guest, who is here supporting the IT. And then Ricky always does a great job of recording and then posting these talks on the SSERVI Analogs Focus Group website after the fact. So there's a whole recording and history of all the previous talks as well. So the focus of this group, the Analogs Focus Group, is to look at both science and exploration in terms of humans and robotics in the solar system and beyond. So today, we're very pleased that Jim Head has joined us, and he will be speaking to us today about some lessons learned and looking at human exploration and robotics, because he has extensive experience in both. And since he's still sending files to Ricky, I will embarrass him with some of his history. So he is the Lewis and Elizabeth Shirk Distinguished Professor of Geological Sciences at Brown University. He's in the Department of Earth, Environmental, and Planetary Sciences. And he has a very long and distinguished career. He started at Brown in 1973. And prior to that, he was working in the Apollo program. He analyzed landing sites, looked at returned lunar sample data, provided training for the Apollo astronauts, and actually worked operations and science support while the astronauts were out on EVA on the surface of the moon. So this extensive experience is obviously highly relevant to this group. He's also, of course, an extremely established planetary scientist. He is looking at the processes that form and modify surfaces, crusts, and lithospheres of planets, how these processes vary over time, and how they interact to produce the historical record that we see today preserved on the planets. He's mastered the art of comparative planetology and has worked on and published on and worked on missions on multiple planetary bodies, the Moon, Mars, Mercury, Venus, Jupiter, Phobos, Earth, et cetera, et cetera. So he has extensive experience there and has done a lot of analog field research as well. Some examples, active volcanoes in Hawaii, Mount St. Helens, volcanic deposits on the seafloor with 3 deep sea submersible dives, which I did not know before, and at least 5 field seasons in the Antarctic dry valleys. And a short story is, one time I saw Jim in the cafeteria at McMurdo Station in Antarctica. And I usually see Jim at science conferences. And I said, Jim, what are the odds of seeing you here at McMurdo? And he says, pretty good, actually. And that's very, very true. It was very funny. So we're very pleased to have Jim here today.
So anyway, thank you very much, Jen. It's a great pleasure to be here. And I want to talk today. The title is Antarctic Fieldwork, Lessons from the Dry Valleys for Human Exploration of the Moon and Mars. And basically, Jen has agreed that I can cover a lot of the different fieldwork areas that we've done in the past, because all of them have messages, okay? So they really tell us a lot about how we do this, why we do it. And really the whole thing is to essentially feed forward to the Moon and Mars, particularly Artemis exploration and the crew training, the crew operations, et cetera. So Jen has very graciously agreed to, excuse me, to let me go through some of these other examples, and then we'll have another seminar following this in the future, in 4 months approximately, in which we'll talk about the detailed application of this to space environments, in particular the moon. We'll use some Apollo examples and then go on to think about Mars as well. It's a lot to cover, so let's press on, and if you could have the first slide, please, I'd really appreciate it. I'll just say next, Ricky, if you don't mind. Are you, let's see, Ricky, are you advancing the slides? Okay, so bottom line here is I want to talk about a variety of things here. I'm going to talk about each one of these in turn. Um, but a couple of them are indeed, next please. What is field work? This is really kind of important because there's a lot of uh, kind of mystic about field work. To me, it's a means to an end and not an end in itself. You always talk about people who, okay, you're not a good field geologist, so you don't have any field work, et cetera. But the whole point about field work is to me, it's a means to an end, not an end in itself. Um, I learned a long time ago that the best geologist is typically the one who has seen the most rocks in the field. So that's really important. It is important. You need to do field trips. You need to do a variety of different things like this. But there's stereotypes that are not too good, okay, from the past, from 50 to 100 years ago, maybe even 25 years ago, in which geologists they basically go outside, bang on rocks, and drink beer with the boys. Okay, geology has been a very male-dominated field in the past, and that's changed radically, which is great. I've done the best I can to try to make that the case. Um, but there's a difference between field training and field work. So the thing is that you do need field training. Absolutely no question about that. You need to go take a field course. I took one at the end of my sophomore year at the University of Wyoming. It was an incredible experience. I took a graduate field course as an undergraduate. It scared the hell out of me, but I took it. I did okay, and I learned a huge amount. And I worked for 4 field seasons as an undergraduate and field mapping in the essentially Appalachian Mountains, et cetera. So getting courses and taking as many field trips as possible is critically important. Um, but the key here is if you want to do field work, you need to have it as a means to an end, not an end in itself. What do you want to try to solve? So, what is the importance of planetary analog field work? First of all, we want to really understand specific off planet geological processes and features that we're not able to do basically without going there ourselves. And sadly, not all of us are qualified to do that or have the opportunity. Jack Schmidt is the only geologist who's actually been able to do that on the moon, and he did an outstanding job. But we really want to look at these and understand these environments, that we have to use these analogs to try to understand the situation as we can study it here on the Earth, because we can't always get to the planets. We also want to study active geological processes to see how they work. This is really critically important, both on the Earth and the planets. So a lot of the things we look at are billions of years old. We're not going to see them happen again directly, but we can look at the analogs and try to understand them then. And we even today to look at how planetary volcanism works. Basically, we can look at a rock, a basaltic lava flow, but that's the essentially crime has been committed. The flow has flowed out. It is solidified. It is sitting there. Okay, and we don't know how it was produced. So even today, field work and active analogs of volcanic eruptions is critically important to understand actually how the process made that product. So we're like crime scene investigators. We're trying to essentially figure out, as geologists, a crime that's already been committed by looking at the geological features. So, hey, when we can see the crime being committed, like an active eruption or active processes, that's really critically important. And that's why field work is so important. Um, Next, please. So there's some dangers in planetary analog field work, okay? First of all, the Earth is not the moon. It's not Mars. One of my favorite lines of all time in the movies was The Wizard of Oz when Dorothy all of a sudden finds she and her dog are in Oz, and she turns, I think it's Toto, says, um, Toto, I guess we're not in Kansas anymore. And boy, is that an understatement. And we have to be careful about that because we're not in Kansas anymore, okay? When we're looking at things on the Earth, we're not on the moon, we're not on Mars, okay? But we're trying to do the best we can. We need to constantly think about how differences in size, gravity, age, and position in the solar system that affect planetary processes really map out into Earth processes. And then there's the dreaded equifinality. I hate that word, but it is really useful. What does that mean? It means that two processes can end up producing the same geomorphic feature. We've seen this with gullies on Mars, okay? Initial studies thought, oh my gosh, these things have to be carved by water. But Francois Forget and his colleagues have shown that, in fact, CO2 and others have looked at CO2 and terrestrial analogs, et cetera, for dunes and CO2 blocks and shown that, hey, these things can also be carved by CO2. So that discussion, because of the equifinality, is in a state of kind of stasis right now, okay? We're trying to solve that problem, but it's a tough one because of that. So we have to keep that in mind. The other thing about planetary field analogs that's a danger is we can almost take them too seriously. If you spend 5 field seasons in Antarctica or whatever, you have a vested interest in making that analog work, and that's a subtle psychological issue, but critically important. So don't get too highly collimated on one example. Next, please. So just thinking of the goals of analog field work, to me, I always try to take a three-pronged approach. First of all, clearly identify the scientific objectives and the scientific questions we're trying to answer. Don't go in the field without a set of questions. Some people say, oh, just go in the field, see what's there. That's okay. That's a field trip to me. But if you're doing scientific research, you want to address a question, it's a means to an end, not an end in itself, the field work. So what questions are you trying to answer? Develop questions, test hypotheses, and develop a strategy and a plan. Know about goals and objectives. Goals, what do you want to get done? Objectives, how do you go about doing it? These are critically important to have in your kit bag as you plan field work. Secondly, science is exploration of the unknown. So, we really need to anticipate the unknown, which of course you can't do. But what surprises will we find? Don't just fill in the blanks of your preconceived hypothesis testing, but ask the question, whoa, stop, look around. What am I missing here? What's different? What did I not expect? Really, these unanticipated discoveries, like Dave Scott on Apollo 15 with the green glass, for example, have really turned out to be fundamentally important. Not what we were looking for at the time, but Dave discovered it, and it has, as we know, found water in it 40 years later in our lab with Alberto Sol, completely revolutionized our thinking about the moon. The third thing is, what do we learn? Or what did we learn? Okay. Getting out of the field, and I try to emphasize this when you give a talk too, debrief. You need to really debrief. And if it went really successfully, that's even more reason to debrief because you want to learn why. Go over why it was successful. If it wasn't successful, find out why, debrief, and then figure out how you factor that into your next field trip. And one of the key things that you need to learn, of course, in these debriefings, is that it's not just about science. And this is where the application of future exploration comes in. Okay. So we need to have closure and think about logistics. How did the logistics go? Not just the science, but the logistics. How did the planning go? How did the training go? Basically, if you have a team, particularly in Antarctica, for example, and you're trying to get this team together, you have to do a lot of training. These are not areas anybody's ever been to typically before in a field party. And so you need to really have training and team building. That's another key thing. When did team building go well? When did it not, and why? And then iterate that back into the next session. So those are the three main uh, things that I would say are the goals of planetary analog field work. Next, please. Let me talk about some examples of analog field work and lessons learned. And this is what I want to spend most of the time on. The last 3 points there, I will generally treat in the next session where we talk about the general guidelines for applications to off-planet exploration and compare the ISS, Moon, and Mars and look at Apollo 11, Apollo 15, and Apollo 16 really in detail to show you what initial studies can do and then scientific expeditions like 15, 16, and 17 were. And then we'll talk about some tasks ahead. How do we implement all these lessons into Artemis for the moon and Mars? Next, please. So let's talk a little bit about some of these examples here, okay? So I want to go through these pretty rapidly, but show you some of the experiences that I've had in the field and why they were important and what we were able to accomplish, goals and objectives, lessons learned, and so on for each of these. Next, first of all, active eruptions at Mount St. Helens and also Hawaii East Rift Zone. These are two really amazing things, two great opportunities. Hawaii is like a laboratory for the study of volcanism. You just basically have to sit around and get a hotline to the HVO, Hawaii Volcanological Observatory, and really figure out what's going on, when the eruptions, when it's building up, and then get there to study the active eruptions. Mount St. Helens is a little more unpredictable, as most Pleiadian eruptions are. But let's press on and take a look at this. Next, please. What kinds of things would we, in fact, do? So here's a way to look at this. Okay, um, basically, um, I look upon these things as reference missions. This is part of the debriefing. How do we apply this to future planetary human exploration planning? So the goals. What are the goals? We want to understand how active volcanoes work because that's when the crime is being committed and producing the rocks that we try to interpret in the record. Of course, we want to mitigate natural disasters, and particularly we don't want natural disasters to happen while we're studying a volcano. Uns- trying to look at the role of input of gases and into the atmosphere and a whole series of other fundamental questions. And where do we go? We go to any active volcano, anytime, anywhere, okay? Because that's where the crime is being committed. Okay, access. How do we get there? Well, typically we use commercial airliners, and then for the last stages, we use helicopters. Okay, and um, that is really the transport of the realm, if you will, and it's critically important. So it's think about this as a mission. You can get to where you want to go for liftoff, but then you have to get in by typically by helicopter. A critical item in all this exploration is infrastructure, and this is really important for uh, the Moon and Mars exploration, and it's something you don't think about on a day-to-day basis. But the infrastructure that supports your ability to do this is really, really important. So, for example, when we go to either Mount St. Helens or to Hawaii, the United States Geological Survey has volcano observatories in both places. They do science, they're great scientists, and they also provide the logistical support. Okay, they help you with how to get there if you're having a kind of an approved, uh, a validated sort of hypothesis or proposal, etc. So that's part of the support. You need this infrastructure. You can't just wander out in the field and carrying all your tons of gear, etc. You need support, logistical support, and this is critical to understand as we think ahead to the Moon and Mars because you have to keep this in mind. It's the logistical support that's enabling the exploration, the operations, the constraints. All these things need to be a part of your plan. Okay, so exploration mode. What do we do and how? Well, we do traverses, just like you would on the moon. Basically, we have a set of goals and objectives. Uh, we try to visit things. We plan traverses from aerial photographs. We do in situ analysis. We do sampling and observations. And we always ask the question, what about the relative roles of human and automated probes? Because if it's easier, you should do an automated probe. If it can do the same thing and you don't have to risk your life, then that's better to do. So these are the questions we ask as we go along. Next, please. If we take a look here at this Hawaii Kilauea East Rift Zone, so we spent a number of months in the 1980s studying the Pu'u uh, oh, East Rift Zone vent and its incredible activity. There were over 40 phases of the eruption. You can see in the upper left here the pyroclastic cone, essentially a classic Hawaiian eruption cone. In the foreground is our camp. Basically, it's known as the Pu'uho Hilton. The USGS has there. It's just literally a box that you can sleep in, and it has a tin roof. And you kind of, when you're sleeping, you can get awakened by essentially rainfall on the top of the tin roof. Sounds really nice, except it's tephra and cinders falling on you. And you can see there we have cameras and monitors for the thermal structure, etc. And then we move up closer and take a look at things like the fountaining. And so we've done studies of fountain height, volatile content. We can measure the volatile content, fountain dispersal. What is the wind doing? Where's the gas going? Fountain optical density. If you lower left-hand side, you can see that some of the outer parts are dark, and that means they're essentially cooling sufficiently before they hit the ground that they behave differently when they hit the ground. So we've been modeling that and putting it into construction of cinder and spatter cone models, and then relating these to dike emplacement events. And then we use these results to model parameters for eruptions, pyroclastic or explosive eruptions for the moon and Mars. So all of this feeds back into that. Okay, next, please. The other thing we do, of course, is go down to the edges of the flow. You can see this perspective view here, beautiful perspective view here, showing the lava flows. We study flow cooling behavior, flow inflation, levee formation, and of course, associated tectonics. I love this one on the left there. It said, something like danger ahead. You can count on that because a little ahead there, the whole road is collapsed down into the valley there. And these are basically flank eruptions of Kilauea that are in fact causing earthquakes, down to the sea earthquakes of the poly. And it's part of the process of dike emplacement and eruptions. Next, please. Okay, so Mount St. Helens. Mount St. Helens, as many of you may know, erupted on May 18th, 1980. It was a paroxysm, whatever it is, the word. It was a huge eruption, okay? The morning of May 18th, 1980, it had been monitored for a while. One could map inflation. And then basically what happened, as you can see in the lower left picture, is that the face of the volcano slid off like a landslide, and that essentially depressurized the magma that was lurking just below, and it exploded and produced a huge lateral and vertical eruption. You can see in the lower right the aftermath of that. That's a view we took looking into Mount St. Helens. Um, After it erupted. And subsequent to the major May 18th, 1980 eruption, it erupted another half a dozen times. Shown on the upper right there is the plume height of the relatively recent activity associated just after in the summer of 1980. So we visited there in the summer of 1980 between these eruptions, fortunately, and we wanted to study the active processes. Nobody had ever really gotten to a detailed emplacement event like a pyroclastic flow or watched the dome grow and explode until this was unroofed and we were able to look inside the volcano and at the actual processes. Next, please. So if in fact we take a look, you can see we looked inside the dome, okay, inside the vent. You can see steam in the upper left coming out. In the upper right is what happens when the eruption occurs, when that explodes, if you will. And then what we're doing here is looking down into the vent, and you can see the brecciated zone building up and inflating, and that's growing and cooling as a function of time. If you look very closely, you can see our precursor party, a couple of people standing on the rim there making gas measurements. Okay, so what happens is this thing expands and inflates, and then a big block will fall off, depressurizing a part of it, and then that will send a shock wave down it, and off it goes again. Next, please. When it does, we can actually see what's going on inside when the column collapses, because when the column collapses, you get these pyroclastic flows, and you can that essentially come down the front of the volcano. Now, here's a view in the middle of looking back up the volcano. This is where we were doing our field work because the column collapses and the pyroclastic flows come down into the surrounding areas, and they form essentially levied pyroclastic flows, which is just what we were trying to look at. Here's a picture of me standing on top of the levee. You have to be careful about going into the flow because it liquefies. It's thixotropic, if you will, because it has a tremendous amount of gas remaining in it. That was a problem we fortunately had anticipated. Unfortunately, one of the US geologists had walked up on top the rim of the levee and walked out on top the flow and had sunk into her waist. She was fine. She got some various numbers of degree burns, but she survived okay. But we knew that about 3 days before we went in, and so we had to adopt some techniques to try to get out and make the measurements we need. Next, please. So when we do look at that, what did we see? Okay, so on the upper left is the plume. It collapses. It sends a pyroclastic flow. You can see the little helicopter in the lower left picture there. That is between the pyroclastic flow initiation and the vent in the upper right. And these things then cascade down, as shown in the lower right, into these pyroclastic flows. They look like lava flows if you step way back, but they're not. But they behave very similarly in the sense of levees and breakout flows and things like that. So again, standing on top of this, in the little inset picture there, you can see what I've just done, which is to step on a fragment inside the top of the flow and gas that little right in the middle of the picture there. There's a tiny little uh, uh, vent volcano there. That's because it's degassing. In fact, if you lie on the side of this vent of the levee there, you can actually put your ear up to the levee and hear the rocks and things clinking and moving inside because in fact the gas is still degassing. That's what we wanted to try to do. So we couldn't get out on top easily, so we got big planks of wood. We had tried to design some metal snowshoes, but we didn't have time to really build them. So we took slabs of wood from the lumber yard and I'd throw that out on top and then jump out on top of that and then kind of ride it, if you will, until it settled down. And then I was able to use the penetrometer to get the physical properties of the flow, et cetera. Um, about halfway through this set of measurements, gee, I smell burning wood. That's because the bottom of the wood was burning. But anyway, it's all good. We got great measurements and managed to contribute to the Mount St. Helens special volume of the USGS and learned a lot. Next, please. Okay, we learned about dome disruption, plinian column formation and collapse, pyroclastic flow and placement, the role of gas and flow dynamics. That was really important. Levee formation and flow behavior. Then we were able to take this again and apply it to understanding explosive eruption on Mars, Venus, and the Moon. It's really been important. This is a terrestrial analog that taught us how the process worked. Invaluable in extrapolating this to the planets. Next, please. So let me turn now to Manicouagan really quickly. Manicouagan impact. Everybody knows about Manicouagan, 100 kilometers diameter, great structure, et cetera. Next, please. I'll just show you, emphasizing here, not exactly the results we got. We did learn something about a lot of things. That's Manicouagan there. It's been dammed and flooded by Quebec Hydro. And you can see the space station, it looming just below this International Space Station there. The thing I want to talk about here is, again, logistics and infrastructure. It took us 4 different mechanisms to get into the central lake there, so that we could study the central uplift and also look at the impact melt sheet and the blocks in there and the viscosity relationships that caused them to be able to be where they were. So the first thing we did was we flew commercial to I think it was Ottawa, and then we took a DC-3. I never knew they existed. Was actually one of the most interesting experiences. You get in the back and you have to climb uphill. I recommend getting a ride on one of these things if you ever have the chance. I don't know whether there's any left or not. Then we went to a small town, where the DC-3 landed, and we got into a Twin Otter pontoon plane, and we flew into uh, Manicouagan. And the key here is that, this pilot was a bush pilot, is really, really good. So when you come in these kinds of things, you come in face up because you want the pontoons to slow you down. The thing about Manicouagan is they flooded the thing, so there's big timber logs over the whole thing, it looks like. So you're coming in and there's like, how are we gonna land on all those logs? Well, don't worry, I can see out the front. Of course, he's got the front tilted up. So he's standing up in the cockpit, trying to see what's going on, and we're watching the logs go by out the windows. But it works. These are bush pilots. They know what they're doing. Okay, so we're in the water, but you need to go into the inner part to look at the central uplift and the melt sheet. So you have to get a lifeboat, basically a large lifeboat. You inflate that and you paddle your way in. Okay, so this is unusual logistics, but the point is, it's the infrastructure, it's the logistics. Believe me, you get to know every one of these people because they're, the pilots, et cetera, because they're really the people who are enabling your research. And we learned a lot, and we applied it to lunar craters and basins. Next, please. So let me just briefly talk a little bit about Pacific Ocean seafloor processes. These, again, are critically important to our understanding of planetary analogs. I want to talk about three cruises that I've been on. Um, Two of them involve deep sea submersibles. That would be Alvin and Pisces, and the third one was robotic seafloor exploration, looking at recent eruptions. Okay, next. So when we do look at this, okay, one of the things that we studied, again, going back to this kind of reference mission, what are we trying to do? What is the effect of pressure, of the overburden water pressure on volcanic eruption style? Can pyroclastic eruptions occur at depths in the ocean of 1 to 3 kilometers or more? You'd think the pressure would prohibit them from exploding. And then how do we apply this information to how volcanoes might work on Venus? So access, how do we get there? Whoa, you know, bottom of the ocean floor. Don't bother calling up United Airlines. Okay, they might get you to where you can get on a ship, but of course the whole point here is that you need a research ship and you need a deep sea submersible, not something that every NASA center or university has. Okay, so what kind of infrastructure is needed? Large scale logistical support. This is like a space mission, okay? You need a ship, you need a submersible, you need a crew that knows how to uh, run the ship and pilot it, as well as a submersible crew that know how to operate that. And you need support crews, and you need repair crew, and you need rescue crews. I remember the first time I dove in the Alvin, I went in to pick up our lunches. Okay, so we go down for the day, come back up at the end of the day. Went in to pick up our lunch, and the cook handed me this big bag for lunch, and I said, this is great, but I really just had like some yogurt. I don't eat too much at lunch. And she said, Jim, I'll get you the yogurt, but take the bag. You never know how long you're going to be down there. Oh, okay. We'll take the bag. Got an extra bag? I'll take two bags. Not a problem. The point is here that rescue is a critical part of this too. You're out in the middle of nowhere. I mean, really nowhere. Okay. We didn't see a single ship the whole time we were out. We saw one mast on the horizon. That's it. Okay. So these are really important. Okay. And the infrastructure is absolutely critical, just like in a space mission. And you need to know and understand that infrastructure. You need to learn it because that's what's supporting you, and you can help with that. Okay. So what do? We do scientific dives, we do traverses, just like you would in the field or on the planet, and we sample and do observations, et cetera. And I'll show you a couple of examples of that in a couple of minutes here. And the relative roles, okay, you can call the submersibles human exploration, and they are, okay. They let you get down. They're your field vehicle, basically. But we also, when you're up on deck at night, you also deploy automated probes. You tow sonar, you tow, water sampling, et cetera, et cetera. And, you know, you can't do all this without some serious results and a legacy on this. What do we learn? That's a critical question. So let me just give you a couple of examples here of my experience and how, what I learned from this. Next, please. So I've done two, again, dives here, two cruises for submersible dives, okay, to study seafloor volcanic processes and eruption processes. Okay, one of them is on Seamount 6, which is at a couple of kilometers, 3 kilometers depth in the ocean, just off the East Pacific rise and off the Nazca Plate. And it's a small seamount. And indeed, the second cruise was in the deep sea submersible Pisces, which was to Luhihi, which is about 1,200 meters depth. It's the next volcano coming up. It's just adjacent to Hawaii to the southeast, east, and it is in fact building up. And we were trying to understand what kind of volcanism was occurring at a shallower level and how it was building up as a function of time and what changes there were in the rock types, et cetera. Next, please. Okay, so if you take a look here, this is the research vessel Atlantis. We have to have a ship to go out, and in the aft part of that ship, okay, is a big crane like this that lowers the Alvin over the side. Okay, it takes a couple of hours to prep it. I used to get up really early in the morning. That's probably where I started my really bad wake up early habits because I go help this crew support getting it together. Okay, because I wanted to learn about it. I was going to go down in it and spend the day down there. I really wanted to figure out how this whole thing worked. I would just do whatever odd jobs, like I painted numbers on the weights. The weights are what take it down to the bottom, which they deploy at the bottom, et cetera. Um, so a typical day is you get into the Alvin. They leave the hatch open. They essentially lower you over the side, and you can see that little Zodiac out there with a couple of people who check everything when it's in the water. They close the hatch, and then basically takes about an hour and 15 minutes commute, so to speak, to the bottom of the seafloor, to just sink to the seafloor bottom at several kilometers depth. And basically, the lights go out pretty quickly. And then about, when you have sonar, so you can figure out when you're getting maybe 40, 50 meters above the floor and you turn on lights, okay? And this is the kind of thing you see, these pillow lavas, et cetera. Um, you spend, 6 or 7 or so hours there, and then you essentially, um, they basically, you fill the ascent tanks, the buoyancy tanks, and you rise to the surface. Again, it takes about an hour to come up to the surface. Okay, so that's a field vehicle, that's a field support, and that's your getting down to the bottom. Next, please. So this is what the field vehicle looks like. I mean, this is, it looks pretty big, but you can see the scale there. But the circular feature in the middle is this about 7 foot radius, a diameter actually, sphere of titanium steel, which is of course what's keeping you from being crushed to death. And inside that, you have 3 people, a pilot and 2 scientists, and each one of them has jobs to do. Okay, so you're pretty busy the whole time. The problem with this whole thing is that the pilot is the only one that can see out front. You can see out a side porthole, but you can't see directly in front. So he or she is the one who's doing all the sampling, and you can see the arm, the robotic arm, and then there's a basket in the front that you pick up your rocks or your other samples, drill cores, etc., and you place them inside there. You can see this is my first cache as it got back up onto the surface. You can see the robotic arm and the claw, and these are all the rocks that I collected in the first dive that I went down on this. So next, please. It's an amazing time, basically, and we learn incredible amount, okay? We learn about how hyaloclastic deposits, pyroclastic deposits in these events work, their eruption dynamics. We learn about the volatile content and the volatile concentration processes going from Strombolian to Hawaiian type. And then this was also something that enabled us to do quantitative models for submarine pyroclastic eruptions. That's this paper here in 2003, basically theory and predicted landforms and deposits. And it's a very well cited paper because it provides a framework which you can use to interpret a lot of these seafloor eruptions. And then, of course, we applied it to Venus, where we have similar high pressure environments. Obviously, the temperature is different, the medium is different, but you can allow for that. And it taught us a huge amount. Next, please. So let me press on here. I didn't say anything about the last one here, which is essentially the robotic seafloor exploration, because what we did there was to go out with essentially a robotic submarine and then stay on board and operate with that one. That's kind of like doing perseverance work. Okay, you got that rover up there, it's deployed. You're all looking around, you're planning traverses, etc. That's a good one to come back to at some point here. But I wanted to. Uh, leave some time for a question or two here. So let me press on to Arctic, Svalbard. Next, please. So this is from Mars analogs, okay? Where is Falbard? Svalbard is pretty damn far north. It's about almost 80 degrees north latitude, um, and it's above Greenland, north and to the right of Greenland there. You can see from these maps here. Again, the logistics of how to get there, this is a dependency of Norway, if you will. And so basically we go typically through Norway. This was done in conjunction with Harry Hiesinger and his field team, which was really a great support team and work team. We learned a lot. Next, please. The key thing here is that we were trying to look at essentially Mars meltwater analogs. Now, there's a big difference between the Arctic and the Antarctic. The Arctic has a lot of heating and melting going on simply because the North Atlantic and other things, basically, the waters are warmer, and so the climate is cold, okay? But it's also warm enough for rain to occur and also for melting to occur. So you can see in this map in the lower right, kind of the setting there. There's a small town called New Allison that we ultimately fly into here. And then there's a few buildings and support things there, et cetera, which is great. But then we work along towards the glacier that you can see coming out into the sound there, into these valleys, and we work a whole series of different things. So look at these different analogs. They're just amazing. I mean, they're all over the place, and they are the wet analogs for Mars, if you will. You can see in the upper right, beautiful examples of gullies. Next, please. And so here again, here are that same picture, but blown up a little bit, and you can see the essentially alcoves, the gullies, and the fans. Remind you of a crater interior on Mars. And secondly, you can see here, where's the source of the water? Huh? Yeah, there it is, right there. Okay, so you can study that directly. A great analog. Next, please. The other thing we're studying is the effects of climate change on ice cored moraine melting. This is just amazing. So you can see in the upper left here that there's a fresh scarp there. You know, that basically I wouldn't want to be standing on. Might be me. I can't really see, but this thing is about ready to collapse because the warming, the global warming, as well as just general seasonal warming, in fact, penetrates into the substrate, melts the buried ice that's in this ice core moraine left over from previous glaciations. And you can see in the upper right, there's a slump. Look at the ice, pure glacial ice that's been exposed. Then, of course, it's exposed and it might be even raining a little bit. And so it melts. And that produces beautifully active solifluction lobes, as you can see in the lower right. These things flow together, converge, and form this beautiful solifluction flow going downhill. And this is happening at high rates. So this is something we've been trying to do with Harry Hiesinger and Ernst Hauber and his team. It's just really fascinating. We have a paper which is in review in geomorphology on this. And it has a lot to do. We should be looking for these on Mars. That's what we're trying to do, because these would indicate not only warm temperatures, but temperatures which enabled ancient ice to be exposed and then melted again to produce these solifluction lobes. Next, please. The other thing, what about logistics here? Well, it's interesting. The town of New Allison is our base, but we really spend time away from that, okay? Um, there are some cabins like you see here in the lower left. They're not bad, okay? The reason you really want to have protection like this, you don't want to be sleeping outside because there's another factor in this environment that we don't typically run into, which I'll talk about in a second. But basically, to get along the water, to get to our field areas, we take zodiacs, like you can see in the upper right. That means that you have to have a wetsuit. You can see in the lower right, because if you fall in the water, it's really cold. Trust me on that one. So you need a wetsuit. And then, of course, you have to leave the wetsuit and the zodiac on the shore and then bring your field gear all the way up to your field site, which is typically a few kilometers up into the valleys there. Um, Next, please. Now, one of the problems is that you're not the top of the food chain anymore. And so this is clear and present danger. Polar bears are all over the place. That's a footprint in our camp, in our field site, left overnight. Okay, and there's a cub and a couple of cubs and a presumably a parent of one sort or another. And you can see these pictures of these polar bears. And basically, you're not the top of the food chain. And these are hungry animals, okay? They're hungry animals. So you have to be really careful. And the next slide shows you what we end up having to do, which we don't usually do in a typical, next please, in a typical situation. We have to carry weapons, okay? We have to carry a bolt action high powered rifle. We have to carry a flare gun with a whole different set of flares. And the key is not to shoot the flare up in the air. The key is to shoot the flare in front of the polar bear to scare them away. Don't hit the polar bear. That really irritates them, and you don't want an irritated polar bear. But this is a clear and constant danger. Part of the field training for this is when you get to Falbard, when you get to New Allison, they have a firing range there. Literally, you have to practice marksmanship, uh, lying down, kneeling, standing up, and then they make you run around the range 4 or 5 times and then do it again, because that's the heart rate you're going to have when you see that polar bear. So again, I don't want to accentuate all this sort of thing, but the point is, there are extenuating circumstances, and I can easily imagine that the adrenaline rush that an astronaut might feel on the moon, might be comparable to this sort of thing. Not fear, but just simply the excitement of the whole thing, et cetera. So these are the kind of things to think about, not only when you're doing terrestrial field work, but how does things like this map out to the moon and Mars? Next, please. No polar bears, but think about it, okay? So let me turn now to the last point here, which is the Antarctic McMurdo Dry Valleys and Mars. Next, please. So a key point here is that the Antarctic Dry Valleys, why would you want to go uh, to spend 2 to 3 months freezing, literally, in camping in Antarctica? It's a long trip to get there. You're away from your friends and loved ones. You don't get frequent flyer miles on Royal New Zealand Air Force or Air Force flights. And there's a whole list of things here. I'll let you enjoy that. But the bottom line is, it's a tough environment. I think one of the critical things is that's hurting more and more people now is basically, there is no TV, there is no internet, there are no cell phones, there's no texting, there's no Twitter, which is really kind of a relief when you get right down to it. But some people uh, have withdrawal symptoms, serious withdrawal symptoms. And I'm serious about that. I mean, there's psychology to this whole thing. And so all of these things are really important for us to think about as we work through training the people going to the moon and onto Mars, because this is exactly the kind of environment they're going to have as well. They're not going to have the same modes of communication and frequency of communication that we typically take for granted. The other thing is in Antarctica, first of all, we fly to Christchurch, get our cold weather gear, and then fly military aircraft down to McMurdo. We get our gear, pack it up for 2 months, 3 months stay in the field, and we get helicoptered out to the dry valleys and dumped. Okay. And so we set up tents there. We do not have any capability to take a shower or a bath for 3 months. You can, I'm clean now. It's okay. You can buy me a beer sometime, and I'll tell you all those great stories. It's daylight 24/7, and everything must be recycled. Boy, yeah, everything. I mean, everything. Okay, we take out everything that we brought in. Um, and oh yeah, the bottom line is the beer freezes solid, solid. Okay, so not a happy situation. What you do is you put the beer in a frying pan, beer cans in a frying pan, and you sort of make it like popcorn, okay, on a Coleman stove. You run them around, and then until they're molten enough to that you can drink them. And you don't want to prematurely open one of those things, because then all the beer is all over the inside of the tent. But anyways, it's a long story. But let's get to the science. Next, please. So the key thing here is that we live in temperate regions on planet Earth. We live in mid latitudes, okay, and in the ice-free regions of Antarctica, it's just incredible. It's a completely different environment. Next, please. Let's take a look at this quick and image here, which shows you the distribution. This is a really great picture of the climate zones on the Earth, and you can see all the variety there. Um, and most of them, are in the temperate zones, but there's a couple down at the bottom there with low precipitation and extremely cold temperatures that are the ones we want to look at, because they're the most Mars-like. Next, please. In the Arctic climate, because of the way in which the continents are arranged and how, in fact, the Atlantic Ocean currents go, it is, in fact, such that it's Falbard we talked about. You do get heating and melting, etc. And so you do get not only permafrost features, but you get wet permafrost features like pingos and thaw lakes and polygons, frost sorted stone circles, and things like that. Next, please. On the other hand, um, and Ricky, I can give you a major bet that this isn't going to play here. Um, can you try that movie and see what's going on? Okay. Um, we'll figure this out, and I'll show this next time. But basically, what we're doing is looking at how the going down to Antarctica and going into the dry valleys. Let's just go on to the next one, please. So the beauty of Antarctica is both Antarctica and Mars are currently extremely cold, hyper-arid deserts. They're the Antarctic dry valleys. There's past Mars, and there's Mars today. So this is a really good place. It's much colder than Svalbard is for mean annual temperatures, and so that's why it's so critically important. Next, please. If you take a look here, the dry valleys are, in fact, one of the just a couple percent of the surface of Antarctica that's not covered with snow and ice. Katabatic winds come off the polar plateau, and they warm as they descend. And in fact, they tend to ablate the ice, and that's why the dry valleys are there. Let's take a quick look at a couple of these examples here. Next, please. So here's the dry valleys. You can see the scale there. I've been to virtually all of these dry valleys here and worked in various aspects of these. I had 5 field seasons in Antarctica. It's an incredible laboratory, an incredible laboratory. And the conditions there are very similar to what you would do. It's very isolated. You do not have communications on a minute-to-minute or day-to-day basis, except with Merdu operations, MacOps, where you have to check in every morning. Mac Ops, this is Geo 541, 5 souls, all well. That's it. Okay. If you don't, they'll send out a search party. So that you're safe, but that's it for the communications. Okay, pretty much. Next, please. So just to finish up here with a couple of things, this, glacial processes are incredible. they're coal-based glaciers, they're debris-covered glaciers, they're active glaciers. We see top-down melting of these on the few days a year when the temperature gets above 273 K. It's top-down melting, it's not bottom melting. So it's a big laboratory for the study of coal-based glaciation and top-down melting. Next, please. And if you take a look at the characteristics of the rocks, okay, they Ventifacts, I mean, the wind is really, in fact, well, we've all experienced this in Antarctica. It's just unbelievable how the katabatic winds can operate. Gusts up to 30 meters per second. Trust me, you want to have your tent really with a lot of big rocks around it. Otherwise, it's gone. And then essentially, also what happens is you get this very dry, occasional snowflake pitting on the top of these rocks, which produces things much like what we see on Mars. So again, a laboratory for the study of weathering, both aeolian weathering, but also chemical weathering that goes on very, very, very slowly. And this is something that Mark Salvatore and student at Brown had shown as part of his fieldwork, as part of his thesis, the details of that and how it's so similar to the Amazonian of Mars. Next, please. The thing about the uh, Antarctic dry valleys is that it varies temperatures vary as a function of altitude, the adiabatic cooling effect. And so areas of the upper parts of the dry valleys, like Beacon Valley, are stable upland zones. And then you have an inland mixed zone at lower elevations, and then you have a coastal thaw zone. Next, please. So you can study the characteristics of these three zones, even though the temperatures differ by only a few degrees, but it's like looking at latitude differences on the surface of Mars. So you can see here, no traditional active layers in the upland stable zone, discontinuous effects, mixing of the two, and then a dynamic active layer for parts of the year in the coastal thaw zone. So this is great. All in one field area, we can look at different latitudes and maybe even different history on Mars. And they manifest themselves very, very differently. Next, please. One thing we see is the surface meltwater. There's none in the upper uh, stable zone, a little bit at the top in the midland mixed zone, and then some seasonally in the essentially coastal thaw zone. So again, we can study these three types of processes in one field region. Okay, next. And we're lurching towards a close here. We can look at the way in which these things and the freeze thaw produce different kinds of polygons. So if we want to figure out what these different polygons are doing on Mars, and Joe Levy's really done a masterful job from his Antarctic fieldwork to this, this is the place to go. And then the last one, next please, is in fact putting these things together, all together, so that we can study these various analogs. Okay, so I'm going to stop here and just say that we'll pick up next time on a little bit more on the logistics of this and how we actually can get to this, and then of course go on to the lessons for off-planet investigations, off-planet exploration. First of all, the International Space Station, and then the Moon and Mars, and we'll look at Apollo examples to see how all of this field work and all these ideas and themes map out into how we would implement this not just for astronaut training, but for training of ourselves, as we are typically going to be in the back room, like we were in Apollo, assisting the astronauts. But remember two things. They are going to have the best view of situational awareness. And in fact, they also are going to be very well trained. So our credo in Apollo was train them, trust them, turn them loose, T cubed, okay? And you really want to be able to train the astronauts well enough by taking them to these field analog sites, teaching geology, teaching how to think about geology, because they're going to be the ones that are knowing what's going on. We'll talk about how that worked on Apollo in the upcoming lecture. So thank you very much. Sorry for the problems at the beginning. Ricky and I will square that away before the next time. And thank you, Jen.
Absolutely. Thank you, Jim. That was fascinating. Really appreciate you spending the time with us today. We have a couple of minutes. If anyone has any questions, you can either raise your hand in the participant list, or you can put a question in the chat and I will work to moderate that. So while people are thinking, I have a question for you, Jim. This might be parlaying into part two that we'll talk about in the next seminar. But you made the point about the infrastructure for enabling this field work, which is so incredibly important. Nothing happens without that. So I'm wondering your thoughts on, as we're sending humans to the moon, um, looking at different scientific locations. If you go to different places, you can't build up as much infrastructure, or if you go to one location, you can sort of build up a larger base. And just how your thoughts on balancing that dilemma, so to speak, of trying to access different locations, because you've shown in this talk how there are so many different scientific questions, and then you go to the specific field site that has the proper characteristics for that science, and having infrastructure there versus having a base or something building it up.
Yeah, I think a couple of comments would be that I think what we did with the Apollo astronauts was first take them to general areas. Okay, they were thematic, like Hawaii for volcanoes, or essentially, Sudbury for what's an impact crater. And the critical thing is not just exposing them to the geology and the geological features and relationships and rock types and processes, et cetera. It's really posing the questions and having them think about it. Okay. For example, as I'll talk about next time on Apollo 16, the consensus was that the Cayley Formation, these plains were of volcanic origin. When John Young and Charlie Duke step out of the lunar module, they said, uh, "We're not in Kansas anymore here, folks. These are impact breccias." And so they were absolutely correct. They called it on the first step out of the lunar module, and in fact, proceeded to sample it beautifully, okay, so that they were able to take their geological training, recognize that they weren't in Kansas anymore, and then undertake geological investigations to document everything and to bring back everything. And together with their observations, really, we understood the role of emplacement of base and ejecta. So the, that's the kind of thing I
Right.
think would be good. Both types of sites, if that answers your question. Sorry.
Yeah, no, that's great. We have a couple of questions in the chat. First one is from Suniti. It says, thanks, Jim. What combination of Svalbard and Antarctic analogs may help build a more comprehensive model of fluvial systems sustained by geothermally driven subglacial melting during the Noachian?
Yeah, one of the things I'll talk about next time as we apply this Antarctica to Mars. One last point is testing the model of the cold and icy versus the warm and wet highlands. So I think the consensus in the community is that the Noachian, based on phyllosilicate distribution and also valley networks, open and closed basin lakes, and possible oceans, is that it was warm and wet. What's the question? Okay. Well, the climate models with a faint young sun don't support that. Okay. And you say, okay, it's just another climate model, but you have to take these things seriously because they're pretty robust. And so that's a big question. Where do we go in the field to, in fact, try to resolve that problem? That's why, after several field seasons in Antarctica, I went to the Arctic because, in fact, that was the warmer, wetter situation where glaciation tends to be wet-based as opposed to cold-based in Antarctica. And we're just developing criteria for that now, actually. It's really a very major question. How do you recognize cold-based glaciation when typically it doesn't leave the same kinds of features that wet-based glaciation does? This is a conundrum. I hate to be in a position of saying must be coal-based because there's no evidence that proves it. That's you just don't want to be in that position. But so these are really important criteria, and I think more field work, a comparative of Arctic and Antarctica, are really going to be the key to that. And as for basal melting, I think it's still so cold in the pretty much okay. Certainly today, and probably uh, throughout a significant part of the Noachian and Hesperian, et cetera, that you still have to pile up a lot of ice to get really basal melting. So any kind of recognition of wet-based glaciation, some in Terra Tempe, for example, there's a couple of papers recently that have described possible wet-based glaciation. That's critically important. They attribute it to heating from the rifting, but could it be atmospheric heating? So these are the kind of criteria. We're developing criteria to recognize both types using both the Antarctic and Arctic analogs as a key. So I hope we'll make progress on that.
And we have time for one more question. Which, according to your opinion, is the best analog on Earth for observing the formation of lunar riddles? Which type of volcanism?
For lunar rills,
Mhm.
presumably sinuous rills, right? Yeah.
Sure.
Look-
Yeah.
Yeah. Um, you know, part of the problem is that it takes a lot of different analogs here, a lot of different, because what's the situation? We're trying to distinguish a lava channel from something that might have been created by thermal erosion, okay? So typically the thinking is that high fusion rates create turbulence, and turbulence can transfer heat to the base and cause a lava flow to actually incise into the substrate, creating a sinuous rill. Um, so I think, was the question about the Earth or the Moon? The Earth, I think.
Yeah, which are there good analogs on the Earth?
Yeah, I would any large lava flow, you need to document not just what's going on in terms of lava channel development, but then how that might manifest into thermal erosion and sinuous rills. It's quite possible that I think some of the Archean examples might be really good there. Okay, they're not so active, so to speak, and they're in the rock record, but they seem to, with komatiites, seem to have extruded a lot of lava fast and undergone some thermal erosion. Some Hawaiian lava tubes also have evidence for thermal erosion. So that's something that's being studied in more detail as well in terms of rates and ability to mobilize subsurface basalt, for example, in erosion. Um, so I think one of the things that we need to do, we're working on right now, the Chang'e 5 mission landed in Northwest Procolarum on this EM4 unit. And this is fed by two sinuous rills. Yuchi Kwan, a student from China University of Geosciences in Wuhan, who's currently a visiting student for a couple of years at Brown, has mapped these out and shown that uh, the relationships among them, and we're working on a model to take the petrology of the return samples and the ages and fit that into a model we can test for the formation of these two sinuous rills that characterize the M4 unit. So looking at lunar analogs is not so bad either, okay, particularly when we have samples.
Excellent. Well, thank you everyone for coming to the seminar. Really appreciate it. And thank you, Jim, for your time, and also to Ricky Guest and NASA's SSERVI for supporting this activity. We really appreciate it, and we'll hear Jim's second portion of this talk, focusing on um, humans on the moon, robotics, operations, logistics, etc., at our next seminar, and you will receive emails about that announcement. So thanks, everyone. Have a great day.
And thank you all. And if you have any questions, just send me an email. And Ricky, thanks for bailing me out, as usual.